Okay, hello everyone. Welcome to lecture 7. This is machine learning from data and this is video 1. And in this particular lecture, we will talk about approximation versus generalization. To be more specific, we will dig into something that's known as the VC dimension. As you can tell just by the name, this is derived from the VC bound that we looked at last time. And then we'll try to understand why this is important in terms of the learning process itself. We'll talk about the bias variance analysis and then look at the learning curve. Okay, so let us begin with this lecture, lecture 7. And if you remember, until like last few lectures, what we've been doing until now is that we have had a lot of theory, we've been doing a lot of derivations, and essentially all that has come down to something that is a link between E in and E out, right? And we've been able to establish this link between, even for infinite hypothesis sets, between E in and E out via something that's known as a growth function, right? And this is good. Why? Because we saw that for certain cases, right, that is polynomially bounded, which is good news for us because then we have hope when we talk about feasibility of learning. Okay, so what was this E in and E out? So basically I have like this universe in which I'm trying to find some answers, right? So that's like my entire data somewhere, and what I have is a sample from the same universe, right? And then I can calculate the error in that sample, but I'm really interested in the error in the out of sample, right? In the actual world, in the actual universe. And because I'm like, this is something that I can see, and this is something that like is unknown to me, right? But basically I'm interested in something that I cannot see. Now my theory helped me see through this, despite the fact that I cannot see through this, but with the help of my theory, I was able to establish this link, right? So that's what we did, and we came up with something that looks something like this. Let me write the equation that we derived. The link between E out and E in is through, as I said, a growth function that's in many situations polynomially bounded, and we'll come to that quickly, is log of 4 times m sub h2n over delta. Okay, so what we said was, right, we will either fail, right? There are two possibilities. We'll either fail or succeed. Both can happen. But the good thing about this theory that we've been building is that we can say for sure with high probability which one is going to come up, right? Whether failure or success. What is going to be our outcome? We can say that with high probability, right? So that's the usefulness of the theory. Basically, like the question that's coming to our minds is that why did we choose this theory to establish this link? Well, there are a couple of reasons why we chose this theory. Let me write the reasons down here. So first of all, the very first is reason is that this theory is time tested. That means it has been used in various scenarios and has been tested, and it works really well. The second why we chose this theory is because it helps us create a link, and which is an important point, between between E in and E out. So what I cannot see, I'm able to see through what I can see, right? That's what I'm doing here. And then the third and the most important point I would say is that this theory has relevance in practice, as we shall see going forward, right? So it has relevance in practice. Okay, great. So that's why we've been working so hard on this theory, and that's what we eventually are able to say that we'll fail or succeed, but we know that with high probability. High probability. Okay, so what do we know? What do we know? In our two-step learning process, if you remember, we had this two-step learning process. And the two-step learning process in the most ideal scenario would be something like this, that I'm able to say E in is really, really small, almost zero, and my E out is almost equal to E in. So this is like the most ideal scenario that I would like to see in my learning problem. This is the most ideal scenario. Now, the other thing that could happen is also like this is also possible that my E in is not almost equal to 0. It's really big. And my E out is almost equal to E in, well, through this equation here, right? I'm able to establish that. What this means is that we've come to this conclusion that this is obviously my in-sample error is really large. So that means like whatever I've learned is not good, right? It's not good, but I know that it's not good, which is also fine. So although this is like we would like to be in this ideal zone, this ideal situation, but even if we've come to this, the theory itself helps us understand that, okay, whatever we learned is not that useful, right? Because I have a huge in-sample error. However, I'm able to peek into the outside world and say that, okay, these are close, but that doesn't really help because my error is really, really large. So basically we haven't learned, and we know that we haven't learned, which is good. Okay, what the theory is good, the scenario that the theory will help us avoid, if you think about it, is this, that I get an E in, which is like the in-sample error, extremely small, right? Like almost 0. And then my E out was actually really big. So basically, I'm like kind of fooling myself in this case if I were to believe this, but my theory would not allow me to believe this, right? Because I have this sort of link that exists between E in and E out. So basically here I'm fooling myself by saying that my in-sample error is really small. So I'm thinking that I've learned, but actually I haven't, because I haven't really created a relationship between something that was unknown, and I'm more interested in that, right? So this is like a really bad scenario, and my theory is going to help me avoid this, right? So that's why we've been doing whatever we've been doing until now. So it helps us avoid this, right? Because I would easily be able to figure out that this is the point where I'm actually fooling myself. Okay, so these are some of the benefits. This is like the theory of learning and its relevance essentially. And then moving on, let's look at the formula that we derived and also look at how that is useful, how that is going to, like, what role is it going to play depending on the size of my data set and the number of points in my data set essentially. This is what we looked at last time, right? So this was our basic equation for probability, good and bad, both cases. But I'm more interested in this relationship between E in and E out versus the error bar, which sometimes we also denote by omega, right? So this formula holds essentially for any hypothesis set, for any function, for any distribution, and any algorithm, right? So this is like a generic formula that exists and that helps us create a relationship between E in and E out with a high probability, right? So with at least 1 minus delta. That's how we at least like to put it. Now, what's going on here is that we, as you can see, we have this m sub h of 2n, and we discussed that quite a bit in the previous lecture. The good news about this is that for certain types of hypothesis sets, this is polynomially bounded. So as you can see, this is a polynomial, which is a good news for us because I'll show you in a bit why this is good news for us. And if you remember, k is my breakpoint, right? So the number of data points that this h cannot shatter, right? So that's what my breakpoint was. And k is my breakpoint, so k stays in that polynomial bound, but that's all good. Okay, so what we really looked at is that there are two kinds of hypothesis sets, two kinds of hypothesis sets. The first ones were the bad ones. If you remember, the bad ones were where all of them could be implemented, right? So m sub h of n was exactly equal to 2 to the n for all n greater than or equal to 1. Why was this bad? Because if you look at our omega, and then let me remind you, this omega, I'm calling the error bar omega just for short, right? And if you just substitute the value for the growth function, like 2 to the, in fact, in this case, it's going to turn into 2 to the 2n, right? So 8 over n log 4 2 to the 2n, right, over delta, right? This is the equation, 4 times, oops, yeah, right? So let's think this is this, but what happens when I kind of expand this equation here? If I'm going to expand this, and obviously I can have a plus here or like have some term in addition to this, But basically what I'm going to have is like this n will anyways come out, right? So this is going to become really like this is going to become independent of n, and then I'll have this like big term that will not come equal to 0. It's going to be big. It cannot go to 0. So that means in these bad hypothesis sets, we do not get a useful link between E in and E out, which is our goal in always when we are like looking at a learning problem. So this was the bad hypothesis set. The second one was the good one, in which M sub h of n was polynomially bounded, right? So the good ones were good. Why? Because again, we care about the error bar omega, right? So first of all, the polynomial bound looks something like this. M sum h of n is less than equal to I equals 0, and k, remember, is the breakpoint, and we looked at this, is n choose I. It is again less than equal to n of k minus 1 plus 1, and of course 1 is a constant, so we can say this is like almost equal to n of k minus 1, where k is a breakpoint. Basically the number of data points that h can the hypothesis set cannot shatter, right? If we substitute this value, let's say n k minus 1 in omega, let's try doing that, right? What happens is it's 8 n log 4, and then this is 2, let me quickly see, m sub h 2n. Okay, so instead of n it's going to be 2n, right? So 2n k minus 1. Well, regardless of that, what's going to come up is omega equals some value here, like some constant log, let's say 8 k minus 1, and some other terms, of course. But basically what I care about is this like log n over n. Why do I care about this? Because for large n, this will tend to 0, right? For sufficiently large n, this goes to 0 as long as I have a breakpoint k. I can guarantee this, because as long as I have a breakpoint, then only I can guarantee the polynomial bound for my growth function. Okay, so this is really useful, because using this definition of my breakpoint and the fact that if the breakpoint exists, we can guarantee some kind of a good relationship between E in and E out. So based on that, we define something that's known as the VC dimension. And the VC comes from the VC bound itself, right? So it's something that we define in a more formal way, and that it is essentially using this concept of a breakpoint only, and that's known as the VC dimension. So let me write the definition. The VC dimension of a hypothesis set H, I'll just write H, is 1 less than the cheapest breakpoint. What is this cheapest breakpoint? So if you remember, breakpoints are essentially points above which like you cannot shatter anymore, right? So the cheapest is the smallest breakpoint. So, or you can say smallest breakpoint. So basically this VC dimension is denoted by D sub VC, and it's nothing but this K star minus 1. Why am I denoting it by K star? Because I'm saying this is the smallest breakpoint. So this means that the VC dimension is the maximum number of data points that can be shattered. So in other words, max number of data points that can be shattered. Okay, so that describes, so why is this important? Now, if you think about it, if my n, the number of data points, is less than or equal to my VC dimension, that means, so that means H could shatter your data, right? This is what this means. H can shatter my data. And if it's the other way around, that means if n is greater than the VC dimension, H cannot shatter your data. It's as simple as that. So it's like a better way of utilizing the value of my breakpoint. So it cannot shatter your data, and I'm going to shatter your data I'm going to summarize these points here. So basically, in summary, we could come up with the polynomial bound for the good hypothesis sets, right? And this, which was like almost equal to n sub k minus 1. And this is the tightest bound, as I said. Why? Because it is obtained at the smallest breakpoint, which we are denoting by k of like k star, right? So basically, we have defined something that's known as a VC dimension, which is nothing but the tightest breakpoint minus 1. And the VC dimension is the largest n which can be shattered, right? And we just said, so that means if n is less than my VC dimension, you can shatter your data, shatter those endpoints. And if n is greater than my VC dimension, then that means n is a breakpoint for h. What does that mean for my growth function? It means this for my growth function, right? So my m sub h of n is less than equal to here, because like this I'm replacing by my VC dimension, right? So instead of k minus 1, which could have been like k star minus 1, this is n to the d like VC dimension plus 1, which is nearly equal to n to the VC dimension for all obviously good hypothesis sets. And what does that mean for the relationship between E in and E out? Because we've been really interested in understanding that, right? So what that means is the error bar, which was this omega term, is of the order VC dimension times log n over n. Again, for the good hypothesis sets we're talking about, right? Which can be shattered. So for all good H, this relationship holds true. Okay, so here I'm going to end this video here. In the next video, I'm going to talk about some examples and sort of try to build a relationship between VC dimension and different hypothesis sets that we've looked at and go from there.